In this problem solving session number 6, we are going to first solve some problems related to squeeze states. Then we will solve problems based on topics we learned from our previous lectures prior to the one on squeeze states. As a first problem, let us consider this. You are given a Hamiltonian, squeezed Hamiltonian in this form, which we have discussed in the last class. Here, omega is the frequency of the oscillator, capital omega. Z is a free parameter. A dagger and A are the creation and the annihilation operator. And you are asked to show that this annihilation operator, which is obtained due to the unitary evolution of this annihilation operator A, you are going to get this expression that A of t is equal to A of 0 cos hyperbolic r plus A dagger 0 e to the power I theta sine hyperbolic r, and here r is the squeezing parameter. So let us solve this problem. However, solving this problem rather than using the so-called Becker-Hausdorff formula to explicitly do this calculation by working out all this, I am going to take the approach of the Heisenberg equation of motion because the time evolution of the annihilation operator is involved. So let me write down the Heisenberg equation for this annihilation operator, and you know that is I h bar dA dt is equal to commutation A and the Hamiltonian, where this Hamiltonian is the squeezing Hamiltonian. Now let me put the expression for this squeezing Hamiltonian here, and that is equal to I h bar omega z A dagger square minus z star A square. And now we have to do the operator algebra. So this I can now write it. I will get two terms. Let me take this term as this. I can take I h bar omega out, and here I have A, then I have A dagger square, and then I have another term that would be minus I h bar omega z star commutation A and A square. It is obvious that this particular commutation is equal to 0, and now I am left with only this to work out. To do it, I am going to use the operator algebra. You know that this one I can now write as this. I have A dagger plus A dagger A dagger. I can now write it like this. And you know that A dagger is equal to 1. So this is going to give me twice I h bar omega z A dagger. So I get I h bar dA dt is equal to this equation I get for the annihilation operator. Similarly, I can get the equation for the A dagger operator, that is going to be dA dagger dt. But however, rather than writing it, let me write it in a simple, let me get rid of I h bar is common both sides. So let me write it as dA dt is equal to twice omega z A dagger, right? This is what I will get. Similarly, you can get the evolution equation for the A dagger operator, creation operator, and that is going to be dA dagger dt is equal to twice omega z star A. So you are now having two coupled differential equation, first order differential equation, and one can very easily solve this. And to do that, let me just take the time derivative of the first differential equation. So I will get this second order differential equation here. I get 2 omega z dA dagger dt, and dA dagger dt I can put the expression from the second equation. I have here twice omega z star A, and from this I get d2A dt2 is equal to 4 omega square mod z square A. So this equation I get, and this is a constant parameter, so let me write it as lambda square A, where lambda square is equal to 4 omega square mod z square. Now you know that the solution of this differential equation is a very standard one, so you will get a of t is equal to, say, alpha cos hyperbolic lambda t plus beta sine hyperbolic lambda t. You are now left out with finding out what is alpha and what is beta. To find that, let me take at t is equal to 0, I have a of t is equal to a of 0, obviously, and putting this in this equation, so you immediately get that alpha is nothing but a of 0, annihilation operator at time t is equal to 0. Now we have to find out beta. To do that, let me take a time differentiation of this equation here, and that is going to give me a dot t is equal to alpha lambda sine hyperbolic lambda t plus beta lambda cos hyperbolic lambda t. And also from the first order differential equation that we have worked out for a, that means this equation, I can write it as twice omega z a dagger t, right? Now if I put, say, t is equal to 0, at t is equal to 0, a dot at t is equal to 0 is going to give me lambda beta, right? And this is equal to, if I now use this equation, right, using this equation, I have simply twice omega z a dagger 0. And I hope you are getting the idea now. Now lambda also, lambda square I have from here, this is what I have, let me write here, because I have lambda square as 4 omega square mod z square, I can take my lambda as twice omega mod z. So using this, I have twice omega mod z lambda beta. Here I have my beta, that is equal to twice omega z a dagger 0. So you see, therefore I have mod z beta is equal to z a dagger 0. Now taking z is equal to mod z e to the power I theta, we can immediately see that beta is equal to e to the power I theta a dagger 0. So I got my beta, and already I have my alpha as a of 0. So therefore, putting the value of alpha and beta, I get a of t is equal to a of 0 cos hyperbolic lambda t. Now lambda I have taken as twice omega mod z, then t, and beta is a dagger 0 e to the power I theta, then I have sine hyperbolic lambda t, so that is sine hyperbolic twice omega mod z t. Okay, now defining the squeezing parameter r as twice omega mod z t, I can write a of t is equal to a of 0 cos hyperbolic r plus a dagger 0 e to the power I theta sine hyperbolic r. And this is what was required to work out, and we have done that. Let us now work out this problem. You are given the squeezing operator in this form, and this already you are familiar with from the previous class. You are asked to find out the position and the momentum operator because of this squeezing operation. Here you are asked to take that this parameter xi is a real quantity, and to do that, let me use the form of the position and the momentum operator in terms of the creation and annihilation operator. We know that x is equal to x 0 point fluctuation into a plus a dagger, okay, and the momentum operator we can write as I am omega. Omega is the oscillation frequency of the harmonic oscillator. X 0 point fluctuation a dagger minus a. Okay, then if I now put this form in this expression, s dagger xi x s xi, and s dagger xi x is now x 0 point fluctuation a plus a dagger s xi. Okay, from this I can get two terms. One would be, let me write it first. I have S dagger xi A as xi plus S dagger xi A dagger as xi. So this is what I have. And you remember from our last class, I listed the properties of the squeezing operator, and one of the properties of the squeezing operator was this. Actually, I have proved it, and this is what you got, that is equal to A cos hyperbolic r minus A dagger e to the power I theta sine hyperbolic r, and the other one S dagger xi A dagger S xi is equal to A dagger cos hyperbolic r minus A e to the power minus I theta sine hyperbolic r. Now let me put these respective expressions in here, and then I will get x is equal to x 0 point fluctuation. If I put those terms here, I am going to get A cos hyperbolic r minus A dagger e to the power I theta sine hyperbolic r, and then I have A dagger cos hyperbolic r minus A e to the power minus I theta sine hyperbolic r. By the way, we are asked to take xi to be real quantity, because xi is equal to, if I take it as r e to the power I theta, now because xi is equal to xi star, so therefore I can take theta to be equal to 0. That means xi is equal to r, and this is going to give me S dagger, instead of xi let me now write r, x s r, that is going to give me x 0 point fluctuation. Here I am now having A cos hyperbolic r minus A dagger sine hyperbolic r plus A dagger cos hyperbolic r minus A sine hyperbolic r. Okay, and let me take A common, x 0 point fluctuation, let me have it here. And then if I take A, let me accumulate the term. I have here cos hyperbolic r minus sine hyperbolic r, then plus A dagger cos hyperbolic r minus sine hyperbolic r. Okay, so I think this is what I am going to get, and this will take me to cos hyperbolic r minus sine hyperbolic r, and I can now write here x 0 point fluctuation A plus A dagger, what you have seen from here. By the way, you know cos hyperbolic r is equal to e to the power r plus e to the power minus r, and sine hyperbolic r is e to the power r minus e to the power r by 2. So here this guy is nothing but my position operator, original position operator. So, and from here I get e to the power minus r x. So this is what we were asked to prove, that S dagger r, not xi now because xi is real, r x s r is equal to e to the power minus r x. So what you see, because of the squeezing operation, the position coordinate is now squeezed, and similarly you can find, because of the same operation, the other coordinate, the momentum coordinate, is getting positively squeezed. That means it's get expanded, and you will have e to the power r p. Let us now work out this problem. This particular problem is very important, and it's a lengthy problem, and I'm going to take you through the various steps to work out this problem completely. You are asked to show that for squeezed vacuum state, the standard deviation in quadrature operator x, which is also called the uncertainty, in quadrature x is equal to e to the power minus r by 2, and uncertainty in the other quadrature, that is y, is equal to e to the power r by 2. And also you are asked to show that in the second problem, that the expectation value of the photon number, or the number of quanta is equal to sine hyperbolic square r, and this expectation value you have to calculate it in the squeeze vacuum state. So let's work it out. So the solution will go like this. You know that the the variance in the quadrature operator is defined as expectation value of x square minus square of the expectation value of x. And similarly for the quadrature operator y, the variance is given by similar expression as that of x. And you already have learned that the quadrature operator x is in terms of the annihilation and creation operator is equal to a plus a dagger by 2. Similarly, quadrature operator y is equal to a minus a dagger by 2y, and therefore you can now find out the expectation value of the quadrature operator x, and that is you are going to calculate in the squeeze vacuum state. And squeeze vacuum state, you know, that can be obtained by squeezing the vacuum by application of the squeezing operator s, capital S xi. And so what I have done here, I have this xi I can get by applying this squeezing operator on the vacuum state, and the other bra part would be given by this part. Okay, then a plus a dagger is sandwiched between them. I am taking half out, and that will going to give me the similar to the problem that we have just solved. In the last problem, you are going to get these two expressions here in terms of a and a dagger, and we already know the properties of the squeezing operator, and we can invoke these two properties of the squeezing operator in terms of a and a dagger. These expressions, if we just put it here you see I have put this expression, and here I have put this expression here, and you can immediately see, because when a is applied on the vacuum state annihilation operator, it's going to give you 0. Similarly, you apply the a dagger operator on the vacuum state from the left on the bra, then that is also going to give you 0. So exploiting these two, you can immediately see that the expectation value of the quadrature operator in the squeeze vacuum state is going to give you simply 0. Then you can find out what is x square. You have to open up these terms, and this is what you are going to get. And by the way, here I have exploited this particular relation that a dagger is equal to 1. So therefore I can now write a dagger is equal to 1 plus a dagger a. Utilizing this expression, I can now write here in this particular form. And if I this way, if I break it up, then I am going to get 4 terms. As you can see, this 4 terms I am going to get. The last term is anyway, it's because the squeeze state has to be normalized, so this is going to give me 1. And here I am now going to work out all these terms term by term if I evaluate it. So first of all, let us evaluate this expression, and this one can be done again. You see, I have written everything in terms of the vacuum state. So let us work out this particular term. This working out all these terms is very important, because it is going to be used in many problems, this relationship that we are going to work out. To work it out, we have applied this clever technique, because I know that as S dagger xi is equal to the identity operator. So between 2a square I can write as a S dagger or S dagger. Either way is correct, but here better to use S dagger a. So if I sandwich between that is going to help me to utilize the relation that I already know. S dagger xi a S xi already we know, and that is equal to this. Similarly for this one, I have this one, and if I open it up, it's simple algebra, straightforward algebra. Only thing is that you have to do it bit carefully. Then finally, this is the expression you are going to get. And then you can also work out in the similar way. After working out this for a square, you can work it for a dagger square also, and you will find that is going to be simply the complex conjugate of this term here. Okay, and this is very straight away. You can actually do it explicit calculation you can do, and you are going to get this expression on the right hand side for s dagger xi a dagger square s xi. This is what you are going to get. And then what you are going to do, you also have to work out the other terms. For example, this one you also have to work out, and for that also again the same tactic you have to apply. You have to sandwich this as dagger, because that is equal to identity, and this will enable you to use these properties, known properties of the squeeze state. This is the expression you can put there, and you can expand it, and this is what you will get. So finally you can work out the expectation value of x square by clubbing all the terms together, and this is what already we wrote, right? So then if you put all these terms together and do the calculations, basically do the sum carefully, finally this is what you are going to get. This is what the term you will get on the right hand side. Now you see, if I here, this is the term I have, but to make the thing simple, because squeezing, if I assume that it is happening at and the direction of theta is equal to 0, that means along the x direction, then I have x square is going to be given by this expression, in which I can simplify and write it in this form. And you know, cos hyperbolic r minus sin hyperbolic r is nothing but e to the power minus r, and therefore we have expectation value of x square is going to be equal to 1 by 4 e to the power minus 2r, and therefore the variance in x quadrature is going to be 1 by 4 e to the power minus 2r, because the expectation value of x, the quadrature x, is equal to 0. And from here you can find out, taking the square root, the standard deviation in the quadrature operator will be simply 1/2 e to the power minus r. And similar way you can work out the expectation value of y square as well as y in the squeeze vacuum state, and thereby you can do the explicit calculation, and finally you can find that the standard deviation in the y quadrature is equal to 1/2 e to the power r. In fact, these things can be pictorially plotted here. For r greater than 0, you see that the x quadrature is getting squeezed, compressed, and the y quadrature is getting extended. Okay, this is very clear from here. Now coming to the second part of the problem, you know that the squeeze vacuum is obtained by applying the squeezing operator on the vacuum state. So the number state you can calculate by calculating the expectation value of the quanta, or the photon number. If I talk about squeeze states of light, then you can find it out by calculating the expectation value of the number operator in the squeeze vacuum state. And number operator, you see it is a dagger a, and already we have worked out this particular expression. You see, now this already we have worked out, and you can straight away utilize it. And if you utilize it, then you are going to get, it would be that expectation value of the number operator, or the average number, or the mean number of quanta, or mean number of photons in the squeeze state, is going to be sin hyperbolic square r. By the way, you are calculating the mean number of photons or mean number of quanta in the squeeze vacuum state. You know that the vacuum state has 0 number of photons, but the squeeze vacuum state, as you can see from here, is that it is actually non-zero. There is a finite number of quanta in the squeeze vacuum state. Now let us work out this particular problem. Here we are introducing the coherent squeeze state, which can be defined as what is done here. First, you create a squeeze vacuum state by applying the squeezing operator, and then this squeeze vacuum state you displace by applying the displacement operator. And already you know from the lessons on coherent state that coherent state is nothing but displaced vacuum state. So here you are having a displaced squeeze vacuum state, and that is called coherent squeeze state. So this is how this coherent squeeze state is defined. Now using this coherent squeeze state, you are asked to find out, in the first part of the problem, find the expectation value of the number operator or the mean number of quanta in the coherent squeeze state. and then you are asked to find out the standard deviation in the quadrature x and y in the coherent squeeze state. So this is again, the calculation is bit lengthier, so let me take you through the various steps, but straightforward calculations. So first work out this quantity, mean number of quanta or mean number of photons, if we talk about coherent squeezed vacuum state in the context of light. Then I just put n, this is the number operator is a dagger a, and this part I can now write in terms of the vacuum state get 0, and this bra part I can write in this form. And here you will see this property of the displacement operator will come very handy, and we have to work out first this term. Okay, this term can be worked out, and this can be done by, again, the usual tactic that we are going to use is we are going to send to is d dagger, because we know that d dagger is identity operator. So utilizing this, I can use the property of the displacement operator, and we see that d dagger a d is equal to a plus alpha, and d dagger a dagger d is equal to a dagger plus alpha star. And then if I expand it, if I expand the terms, this product, then this is what I am going to get. Okay, and therefore I have the expectation value of the number operator. I have this d dagger a d alpha term I have worked out, and I have put it here. And then we are having everything in terms of s dagger and s operator here, and we are going to get 4 terms. And already we have worked out various terms in the previous problem, and we can straight away utilize all these results that we worked out in the last problem. And last term, as you can see, s dagger, this term is going to give you simply mod alpha square. And if you have utilized the properties of this squeezing operator, and we have calculated all these things explicitly in the last problem, utilizing all these things, you are going to get sine hyperbolic square r plus mod alpha square. So that is going to be the mean number of quanta in the coherent squeeze vacuum state. Similarly, you can calculate the variance in x operator as well, and variance in the x operator, again you are writing this, you have to first calculate the expectation value of the x quadrature operator in this coherent squeeze vacuum state, and you can write this whole term in this form. And utilizing the properties of the displacement operator as well as the squeezing operator, you will going to get expectation value of the quadrature operator in here is going to be mod alpha. You see, in the earlier case, in the case of the squeeze vacuum state, the expectation value of the quadrature operator x was 0, but here in the coherent state, coherent squeeze vacuum state, you are getting a non-zero number, and that is equal to mod alpha. And x squared also you can calculate it, and utilizing all the properties that we have already worked out. And here only thing is that you have to now work out this particular term, say d dagger alpha a square d alpha, which also can be worked out by applying the similar tactic. You have to sandwich d dagger in between, and thereby you can very easily work out d dagger alpha a square d alpha to be this, and then putting this term here in this expression. Okay, here if you put it there, then you are going to get this term on the right hand side to be e to the power I theta cos hyperbolic r sin hyperbolic r plus alpha square. Similar way you can calculate for the a square part, and this is what you are going to get. This is simply the complex conjugate of this particular term, as you can see here. And then you can also have to work out a dagger a part, and that is going to give you this term, which already we have worked out. And then putting all the terms together, combining all of them, you will get x square term, expectation value of x square to be like this. And Then if you do the algebra, this is the final term you are going to get, and after simplification you are going to get this expression, and eventually that is going to give you that the variance in the quadrature operator for the coherent squeeze state as a coherent squeeze vacuum state is 1 by 4 e to the power minus 2r, and the standard deviation in the quadrature operator x is this, and in fact you can see that this is actually the same as that of the case of squeeze vacuum state as well, and similar expression you can get it for the y quadrature as well, that is 1 half e to the power r, and this can be now pictorially drawn here in this plot. What is the difference between that of the earlier one is that now you see that squeeze vacuum you had, and now that squeeze vacuum state is now getting displaced along the theta is equal to 0 direction, and this is what you are getting. But as I have already shown you that the amount of squeezing in the x direction, x quadrature, and amount of expansion in the y quadrature is exactly the same as that of the squeeze vacuum state. But if now I take theta to be along a different direction, then this is the plot you are going to get. Here also the amount of squeezing is in the x quadrature as well as in the y quadrature is going to remain the same. Only thing you see, now the squeezing is happening in a particular direction in the phase plot. Now, having worked out a couple of problems on squeeze states, now let us go back to our earlier lectures and do some problems based on those lectures. Let's do this problem. Here you are asked to show that the Hamiltonian for a plane electromagnetic wave propagating in free space can be expressed by this Hamiltonian. H is equal to twice epsilon 0 E0 of t mod square into V. V is the volume. For this, please refer to lecture number 18 of the course. And there you remember while we discussed about the propagating plane electromagnetic wave, we have written down the electric field for the plane electromagnetic wave in free space in this form. E is the electric field. E of RT is equal to eta, this is the polarization direction. E0, this is the amplitude of the electric field, and then we have e to the power I k dot r minus omega t, and then you have to, because the electric field is real, so it has to also be followed by complex conjugate. Or we can also write it just like this, time dependent part we can put it in the amplitude E0 of t, then we write simply e to the power I k dot r plus complex conjugate. Okay, now you know the Hamiltonian for a electromagnetic wave, which basically represents the total energy of the electromagnetic field, can be written by this formula. H is equal to epsilon 0 by 2. We are considering free space propagation, so d3r e square plus c square b square. So this is the total energy or the Hamiltonian. Now in free space, this term and this term are equal, so therefore we can simply write this Hamiltonian as epsilon 0 e square d3r. Now to evaluate this integral, let us consider a volume element in free space, and for that let me consider a cubical box, and where this box, each side of this cube has equal length, and say length is, let me just draw it first, say each length is equal to L. Okay, say this is my x-axis, this is my y-axis, and this is my z-axis or z-axis. Now volume is obviously is equal to L cube. Okay, now to be more specific, let me take the electric field to be polarized along say x direction, and its amplitude is E0 of t, and let's say this electric field is propagating along the y direction, and then we'll have this as my electric field expression. This also I can write because of the fact that electric field, this amplitude is a complex amplitude, so let me write it is as mod of E0 of t e to the power I phi e to the power I ky plus complex conjugate. I can also write the electric field expression in this form. E is equal to x cap, the polarization direction of electric field, twice E0, okay, cos ky plus phi. Alright, so this is what my electric field expression is. Now, as it is a propagating wave, we must have this boundary condition, electric field at y is equal to 0. You see, I am taking, this is y is equal to 0 and this is y is equal to L. I am taking the boundary condition. I should have that the electric field at y is equal to 0 should be equal to electric field at y is equal to L, and therefore I have, if I just put the electric field expression here, so you will get, I will have cos phi is equal to cos kl plus phi, and if I break it up, if I expand it, then on the right hand side I have cos kl cos phi, okay, minus sin kl sin phi. So this is, immediately I can conclude from here that I must have sin kl is equal to 0, and that means I can also write it as sin m pi, where m is an integer. It implies that you have kl is equal to m pi, okay, and because of the fact that k is equal to omega by c in free space, because the refractive index is equal to 1 there, so if I put the value of k is equal to omega by c, then I can write omega m is equal to m into pi c by L, okay. This is the expression for the angular frequency of the wave, and as you can see, the frequency is getting discretized because of the boundary conditions. Now, without loss of generality, I can take phi is equal to 0, and if I do that, then I will get the electric field expression E is equal to x cap twice E0 of t, this is the modulus of the amplitude, and I have cos ky. So now let us do the integral, because I have the expression for the electric field. So epsilon 0 E square d3r, if I put the value of the electric field, this is a triple integral, so I have my here dx dy dz, x goes from 0 to L, y goes from 0 to L, z goes from 0 to L, and I have here 4 E0 t mod square, and I have cos square ky, and you know that integration is going to be along the y direction. Dx and dz integral is going to give you simply L square, so let me take all these things out which is not involved in the integral. So I have simply this integral I have to evaluate, cos square ky dy, and you know cos this can also be very simply written in this form. I can write cos square ky as 1/2 0 to L 1 plus 2 cos ky dy, and if I solve it, and also keep in mind that I have this boundary condition that I have to use this kl is equal to m pi. Because of this, if I solve this, and immediately I will get twice epsilon 0 L cube E0 mod square, and this also I can write it as twice epsilon 0 E0, okay, because this amplitude, this time dependent amplitude, and L cube is V, volume. So this is what was required, and this is what was asked to prove. Let us now work out this particular problem, problem number 6. This problem is similar to the one that just we have done. you are asked to show that the Hamiltonian for a standing electromagnetic wave can be written in this form, where H is the Hamiltonian, H is equal to epsilon 0 n square V mod alpha square. Actually, this form of the Hamiltonian we encountered in lecture number 18 of the course, and there I just have obtained this without explicitly doing the calculations, and I asked you to do that. Let me work this Hamiltonian out by explicit calculation. To do that, let us write down the Hamiltonian for the electromagnetic field. The general Hamiltonian is in free space. It is epsilon 0 by 2, the volume integral E square, okay, plus C square B square. Now, just to keep in mind that here we are not considering a propagating wave, rather we are considering a standing wave which is confined between two plane mirrors, which is separated by a distance of L, and let's say the standing wave is formed along the z direction. One mirror is placed at z is equal to 0, the other one is placed at z is equal to L. And to consider the volume element here, we are going to consider the length perpendicular in the perpendicular directions to this mode axis. Okay, this is along the z direction, the mode axis is along the z direction, and perpendicular to it, that means along the y and the x direction, we are going to consider the length element, and then the volume is going to be V is equal to L into L perpendicular square. Because of the two transverse direction, that is x and y, we have L perpendicular square along them, and therefore the volume element is going to be L into L perpendicular square. We are considering, as I said, standing electromagnetic wave, and we have discussed about in lecture number 18, and I don't want to repeat it once again, but you know that there we have written the electric field expression as E is equal to eta. Eta is the polarization direction, E of t is the complex amplitude of the electric field, sine kz, okay, and the corresponding magnetic field was B is equal to k cross eta. K is the wave vector and eta is the polarization direction. A of t is the amplitude of the vector potential, and we have here cos kz. This is the expression for the magnetic field. And the boundary conditions are, because the electric field has to be 0 at L is equal to 0, and at the other end of the mirror, that means at the other mirror which is situated at the z is equal to L. So this is what you should be, both of them should vanish, electric field should vanish, and because of the expression of the electric field, we can then write that we are going to have sine kl should be equal to 0, which is equal to sine of into m pi. M is an integer, and this implies that kl is equal to m pi, and that means this wave vector is now discretized because of this boundary conditions. Kn is equal to, actually I should write m here because I have integer indices I am taking to be m. Okay, so km is equal to m into pi by L. So the Hamiltonian, therefore I can now write as epsilon 0 by 2. This Hamiltonian, I have to put down the expression for the electric field and the magnetic field, and if I do that, then I am going to get epsilon 0 by 2, and I have E of t square sine square kz plus k square c square, okay, a square cos square kz. I am simply putting the value of the electric field and the magnetic field here, expressions that just I have written. So this is what I am going to get. Now integrating, because it's a volume integration, so I have epsilon 0 by 2, integration along z is 0 to L, along x would be 0 to L perpendicular, along y it would be 0 to L perpendicular, okay, and then I have these expressions once again, E square sine square kz plus k square c square a square cos square kz, you have here dx, dy, dz, and these integrations I think you can very trivially work it out. You will have epsilon 0 by 2 L perpendicular square, and then you will be left out only one integration 0 to L, and that would be E of t square sine square kz plus k square c square a square cos square kz dz. And if you do this integration, you are going to get epsilon 0 by 2 L perpendicular square L by 2. This is going to give you L by 2. This is going to give you L by 2 if you do the integration. And then you are going to have here E of 0 t square plus omega square a square, where I have used the fact that omega is equal to kc. Alright, and this is going to give me epsilon 0 by 4 into volume. Okay, and then I have E0 t square plus omega square a square. Now introducing the parameter alpha, as we have I think done this in lecture number 18 also. I have defined what is this parameter alpha. Alpha is equal to 1 by 2n, where n is a constant quantity, omega a minus ie. If I introduce that, then I have mod alpha square is going to be 1 by 4 n square omega square a square plus e square. Okay, and this means, because I have now, you see, this I have here and this is I have here, so using this I can now write my Hamiltonian H is equal to epsilon 0 n square mod alpha square into volume, and this is what was required. Let us now work out this problem. In this problem, it is given that a light beam of wavelength 633 nanometer and power 1 femtowatt is detected with a photon counting system of quantum efficiency 20% with a time interval of 10 millisecond. You are asked to calculate the count rate, the average count rate, and finally the standard deviation of the count rate. So let's do it. This problem is based on what we have discussed in lecture number 19. There we found that the photon flux is given by this formula. Phi refers to the photon flux. It is equal to power divided by h bar omega, where h bar is the reduced Planck's constant and omega is the angular frequency of the beam. Okay, angular frequency of the light beam. Now you can write h bar omega as sc by lambda, and you can calculate this quantity because all the quantities are given. H is equal to 6.626 into 10 to the power minus 34, and c is equal to 3 into 10 to the power 8 meter per second, and lambda is 633 nanometer, so that would be 633 into 10 to the power minus 9 meter. And if you do the calculation, you are going to get it as around 3.14 into 10 to the power minus 19 joule, and in terms of the electron volt, this is going to be around 1.96 electron volt. Okay, and power is given here as 1 femtowatt, so P is equal to 10 to the power minus 15 watt. So if I put the values, all these values in the formula, then photon flux is going to be, you can calculate it and you will find it to be 3.2 into 10 to the power 3 photons per second. Okay, this is the photon flux. Now in lecture 20 we learned that the count rate is given by this formula. R is equal to quantum efficiency into the photon flux. So here quantum efficiency is 20%, that means eta is equal to 0.2, and photon flux is 3.2 into 10 to the power 3 photons per second. So this is going to give us the count rate as 640 counts per second. Okay, Now let us do the second part of the problem. In the second part of the problem, you are asked to find out the average count value. Again, we have written down this formula in lecture 19 that the average count value is given by count rate r into the time interval between photon counting, and that is given to be 10 millisecond. R is 640 and t is 10 millisecond. That means 10 into 10 to the power minus 3 second. So this is going to give you the average count as 6.4. Now the third part of the problem, the standard deviation in the count value. Now you see it is also given that this light beam is going to follow the so-called Poissonian statistics. So we know that from Poissonian statistics that the variance delta n square is equal to mean or the average photo count, that is n, or in fact in this case this is nothing but n of t in this particular problem, and that is given to be 6.4. So therefore from here you have this standard deviation delta n is square root of 6.4, and this is be nearly 2.53. Let's now work out this problem. Problem number 8. A pulse diode laser operating at 800 nanometer emits 10 to the power 18 pulses per second. The average power measured on a slow response power meter is 1 milliwatt. On the assumption that the laser light has Poissonian photon statistics, calculate the mean photon number and standard deviation per pulse. Okay, let's do it. Again, this problem is also based on what we have learned in lecture number 19. So to work it out, let us understand what's going on. This laser is emitting pulses, and these pulses are emitted at the rate 10 to the power 8 pulses per second. Okay, in 1 second 10 to the power 8 number of pulses are emitted, and the average power is given as 1 milliwatt. Okay, to do this problem, first let us find out what is the energy of a single pulse. Now you see the average power is going to be given by energy of a single pulse into the number of pulses per second. So this is how you are going to get the average power, number of pulses per second. Now this number of pulses per second is already given, that is 10 to the power 8. P is also given, that is 1 milliwatt. So you can find out what is the energy of a single pulse, that is going to be P. P is 1 milliwatt, that means it is 10 to the power minus 3 watt, and number of pulses per second is 10 to the power 8. So therefore this energy is going to be 10 to the power minus 11. Energy of a pulse is going to be 10 to the power minus 11 joule. Okay, now the average number of photons per pulse is therefore given by, average number is given by energy of a pulse divided by energy of a photon, single photon, and h bar omega, you can calculate it in the similar way as we have done it in the last problem. Sc by lambda, h is equal to 6.626 into 10 to the power minus 34. C is 3 into 10 to the power 8 meter per second, and lambda is 800 nanometer, so 800 into 10 to the power minus 9. So if you do the maths, you are going to get it as 2.5 into 10 to the power minus 19. Okay, this is what you will get. So the average number of photon, mean number of photon, if you put all these values, it is 10 to the power minus 11 divided by 2.5 into 10 to the power minus 19. Okay, this is going to give the average photon number as 4 into 10 to the power 7. And because the laser light is assumed to obey Poissonian statistics, the standard deviation delta n is simply equal to the a mean number of photon, right? Square root of the, because the variance is equal to the mean number of photons, so this is going to be square root of the mean number of photons. Therefore standard deviation is, if you put the number, square root of 4 into 10 to the power 7 is going to give you around 6.3 into 10 to the power 3. So this is what you are going to get. Now let us go to the next problem. Problem number 9. This I promised in the maybe in the lecture number 20 that I'm going to do this in the problem solving session. Here you are asked to show that for thermal light, variance is equal to mean number plus square of the mean number. So this is little bit calculation is involved, so I'm going through the steps here. And you know the variance is equal to, given by this formula. Here you have to find out the average of n square, and then you have to find out the average of n photon. So average of photon is going to be given by this expression, and Pn is the probability distribution, and probability distribution, you know that this Bose-Einstein distribution is followed by thermal light, and this is the distribution. Pn is this, and we can simplify it by, if I take x is equal to e to the power h omega by kBt, then I just get this very simple looking formula here for the probability distribution. And if I put it in the expression here, then this is what I have to finally work it out. So because summation is over n, so I am taking 1 minus x out, so this is what I am doing. Now you know dx of x to the power n is n into x to the power n minus 1. So if I multiply this both sides by x, then I get n x to the power n. So this is what I am going to get, and this I put in my formula here. Here I am putting it. You see, this is, I'm systematically showing you everything here, so I think you can easily follow the calculation. And then I'm taking the summation inside here, because sum is over x to the power n. So, and this summation, sum over x to the power n, when n is going from 0 to infinity, it's basically series is 1 plus x square and so on. It is an infinite series, so therefore you are going to get 1 divided by 1 minus r. So this is here x, so 1 by 1 minus x. So this is going to give you, if you take the differentiation of 1 by 1 minus x, you are going to get 1 by 1 minus x whole square. So this is going to give you that average number or mean number of photon, this neat formula you are going to get. And in the similar way you can find out n square, again putting the value of the probability distribution here, and you can work this out. This also you can write in terms of this derivative here. It's very simple to show. If you just, I think you can very easily show it, that this is what now I'm utilizing in the summation here. And then again in the similar way, if I do the maths here, this summation is going to give me 1 by 1 minus x. Similarly here you are going to get 1 by 1 minus x, and therefore taking the differentiation, this is what I'm going to get. And then you can see that x by 1 minus x is nothing but average number of photon or mean number of photon, and this is the square of the mean number of photon. So thereby you have worked out what is your n square, average of n square, and then putting the value of average of n square here, and n mean is already known, that is n bar, and that is square. So this is what you will get, and therefore finally the variance of the photon number is given by this expression, and which was asked to get. Okay, now let's go to the next problem. In this problem you are asked to show that for coherent state, the uncertainty in the photon number and uncertainty in the phase, the product of the uncertainties in the number of photons and the phase is greater than or equal to 1/2. So this is a kind of a uncertainty relation. Now let us work this out. I am again taking you through the steps here. You see the average number of photon or mean number of photons in the coherent state can be worked out by calculating the expectation value of the number operator in the coherent state. This I think we have done in the class also. That's going to simply give you mod alpha square, right? and n square you can calculate it. Here you have to find out the expectation value of the number operator square a dagger a with respect to the coherent state. And here what I have done here, instead of a dagger, this if you see, instead of that one I am putting a dagger a plus 1, because you know that a dagger is equal to, this commutation is equal to 1. So that means I can write a dagger is equal to a dagger a plus 1, right? Utilizing this here, I have now two part of here. This is one part and this is another part. This already we have worked out, that is mod alpha square here, as you see. And then this, if you work out, you are going to get mod alpha to the power 4. Then putting it in the variance formula, you are finally getting mod alpha square, and therefore the standard deviation is equal to mod alpha. Okay, so mod alpha is square root of the mean number of photon n bar. Okay, now having working this out, delta n part you have worked out. Now we have to find out what is delta phi. That we can find out by using the geometrical interpretation of coherent state. As you know that the coherent state is nothing but displaced ground state, and this is what you are having. This is the, we are considering here the quantum uncertainty of a coherent state with amplitude alpha. Okay, here this is the mod alpha, this is the amplitude, and as you can see from this plot here, this phasor of the coherent state has an average length mod alpha and makes an average angle of phi, as I have shown here, okay, with respect to the x-axis. And the uncertainty circle has a diameter 1/2. Now you see this mod alpha, which is equal to square root of n bar, is much, if it is much greater than 1, and it is for the coherent state. If I have this mod, I mean to say that if mod alpha is very large, then the phase uncertainty delta alpha is, this is what your delta alpha, as you see from this diagram, that is going to be uncertainty in the diameter divided by alpha, okay, mod alpha, and therefore uncertainty the diameter is around half, and mod alpha is square root of n, which is nothing but delta n. So from here you see that delta n into delta phi, I can write that that is greater than or equal to 1/2. So this is the uncertainty relation in terms of the photon number and the phase. What it basically means is that in the context of coherent state, you cannot find both the, or you cannot determine both the number of quanta and the phase of the coherent state with 100% certainty at the same time. So there is going to be always some kind of uncertainty is there in knowing the number of quanta as well as in knowing the phase of the coherent state.